It gives me immense pleasure to introduce today's first speaker, Dr. Partha Acharya. Dr. Partha Acharya is a distinguished technology leader with over 20 years of experience in IT industry, especially in data analytics, neural network, computer vision, artificial intelligence, machine learning and deep learning, kernel programming, compiler development, and quantum computing. He is presently working with Tata Consultancy Services, Research Wing of Bangalore and Hyderabad as solution architect. He did his PhD from the Indian Institute of Technology, Kharagpur, MTech from the University of Calcutta, and MCA from Vidyasagar University. He has published many papers in reputed international journals and book chapters, and 4 patents in his field. He previously worked with Ava Robotics, Boston, USA, Blaze, formerly Thinsei Semiconductor India Private Limited, Logitech Engineering and Design India Private Limited, VMC Limited, SQL Star International Limited, and MT3 Impacts Private Limited in various capacities. Dr. Partha Acharya has also contributed to academia as computer faculty at the International Institute of Information Technology, Salt Lake, Kolkata. Guest lecture at AICTE Faculty Training for Computer Science Faculties of College, RVR and JC College of Engineering, Guntur, Andhra Pradesh. And he is a member of Syllabus Committee at Ramaya University of Applied Science, Bangalore, Karnataka. May I request Dr. Partha Acharya to start his session.
Thank you, Dr. Chatterjee, for your introduction. So I may switch off my video for bandwidth purpose. Let me share my screen. So can you see my screen?
Yes, sir.
Yeah. So in this short time, that is 1 hour and 30 minutes, I have to go through very complex thing, that is quantum computing, and that too optimizing. The optimization, the entire optimization problem is a very, very complex thing. And that too in quantum field, it makes more complex. So the today's title, as I told, that is optimization in quantum computing. So here I'll be deal with a very small portion of it. That is, I mean, that is what my title of this lecture. So let me first explain you what it is, that is maximum likelihood decoding, and why we need the decoding. So there are actually broad types of distance decoding methods. One is hard decision decoding, another is soft decision decoding. Hard decision decoding takes a stream or block of bits from the threshold stage of the receiver and decodes each bit by considering it definitely as 1 or 0. They usually estimate the Hamming distance. So that is in field of network communication I'm talking about. This could be hard decision decoding, could be for, for other field as well. And soft decision decoding, the soft decision decoding is a class of algorithm that takes the stream or block of bits and decodes them by considering a range of possible values that it may take. It consider the reliability of each received pulse to form a better estimates of input data. Now, I mean, this is something, the difference between hardware and software. The hard decoding means when we are doing it in hardware, and soft decoding, we are doing the similar thing in software. So what I told, maximum likelihood soft decision decoding using, so it's a decision decoding of maximum likelihood. Maximum likelihood means it is a kind of Bayesian identity where we'll be using the Bayesian identity. Any questions? Okay, please mute it. So the way the Bayesian learning, the probability calculation that occurs, that the same thing will be doing the identity iteratively. So to reach some maximum likelihood decoding, to to select a code word which belongs to the to maximizing the probability. So that is what is maximum likelihood soft decision decoding. And now I am coming to the quantum optimization, where I will be using the Grover search algorithm. Now, Grover search, again, that is a very class, I mean, within quantum computing, that is a very, quantum computing is not very old. It's maybe some 60, 70 years old, or maybe little more than that. And there, the Grover search algorithm is bit old within that period of time. And that again got developed and got modified. The modified version of the Grover search algorithm is the adaptive search. That is what I want to discuss about in today's discussion. Now, first coming to something, it may come to your mind, what is optimization, why we need optimization. So if I discuss about the optimization, first I will discuss about the classical methods. Then I will discuss a little bit optimization, what we need, because in today's discussion, I think everyone who is attending knows AIML. So how we optimize, what are the optimizer in AIML? Then I will come to the quantum computing, because that is a very similar what we are doing in AIML. But of course, taking all the constraint and other things of the quantum computing. The classical method. So what we actually mean by optimization. So optimization in mathematics, as we say, that suppose there are different possibilities or different solution of a certain phenomenon. So now how to find out the best solution from the set of available alternative, that is something called optimization. But the problem comes when, these there are three fundamental elements in any optimization problem. One is the objective function, decision variable, and the constraint. So these three are the main uh, unit which actually control the optimization, and on which the entire optimization is standing, just like the Euclidean geometry standing on the axioms. These are something like that. So objective function is, you can say that it's the mathematical formula. You want either maximize or minimize. So sometime in, not sometime in AI we call it loss function or something like that, or the cost function. Suppose I want to find out the profit and loss of something. Then comes some decision variable, means those variables, something like the input. Suppose I want to find out the profit or loss, what will be my capital expenditure, timeline, and all those things. Those are the input I'll be giving. So those are the decision variable which actually guides that optimization problem. And then comes another thing, that is the constraints. What are the constraints? Constraints are actually which the limitation, that tells the limitation and the restriction that must be met. They define the set of available alternative. As for example, my capital expenditure is not more than 1 million. The timeline I'm giving is not more than 1 year, something like that. Now, there are, in my, let me tell you one thing. In the slide, I couldn't write everything. It is not possible to write everything in the slide, but there will be something else I'll be discussing other than slide. And if you have any problem, please stop me in between and please ask me questions. So now, coming to this optimization, there are various optimization like continuous optimization, discrete optimization, depending on the what kind of problem we are dealing with. Then comes the constant and unconstant optimization. So here in this quantum computing, the optimization will be dealing with the unconstant optimization. That means whatever is the optimization problem will boil it down at the level of unconstrained. That means we will remove all the constraint and will make it unconstrained optimization. Then comes the linear and non-linear optimization. So these are the types of optimization we know in classical methods. Now, Coming to optimization in AI/ML. So in AI/ML, we know that the model training, the learning involves weights and biases involving a loss function. The entire AI/ML actually, when we do, we give the input and we see that figures and those things, that is actually representation of a function. And then we do some back propagation, which we call the learning. This learning actually, we do the back propagation or something, actually that is the learning rule. Whatever we are doing there, we are actually doing the optimization to minimize the loss function. This could be reverse in case of reinforcement learning, whatever it is. So there, the common optimization algorithm, we use the gradient descent, stochastic gradient descent, or Adam optimization. That is actually some variation of the stochastic gradient descent. What we do, we find out the local minima. Sometimes what happens, it stops at the local minima. So that is the problem. Then from the local minima, we have to find out the global minima. So that is something here, the finding out the global minima is actually the challenge. So that is something what we'll be doing, or we want to do very easily using quantum computation. So that is the relation between AI/ML optimization, and from it is a, I mean, we are taking forward it to the quantum area. So I didn't step into my discussion, today's discussion. This is just the, I mean, background of the discussion. And other than that, there are certain optimization, like these are called post training optimization, like size compression, accuracies, which are very, I mean, you can say, I mean, today's industries, they are working on it. As for example, suppose we have built the model, but most of the time after training the model, we see the model is very hefty, and then we need to reduce the size of the model, because as for example, sometimes we use something called lottery ticket hypothesis. That is something follows the economics 80-20 formula. 80-20 formula, what is, let me tell you, give you one example. Means 20% of the 80% uh, production from a country or a industry, or from a country, is enjoyed by the 20% of the people. This is something, which is there in the economics. But in lottery ticket hypothesis, what we do, in a model, we have seen that 80% of the model is actually, it's not required. Only that 20% of the model which is lies inside the main actual model, which is actually does the main work. But the problem is how to find out that thing, and that can be done with some reinforcement learning. I mean, that is again, I mean, there is a trade-off between the accuracies and the size compression. So that is something in terms of AI/ML. So now, before coming to quantum computing optimization, please let me know if you have any questions. Yeah, I couldn't understand what you said. Can you come again? Can you come again? Okay, any other questions?
Any question from the participants? Sir, please continue.
Okay, please let me continue. So in quantum computing, optimization in quantum computing aims to use the unique properties of the quantum mechanics. That means whatever we know about the superposition, entanglement, we have to use those properties, and we need to optimize the same the loss function or the function for the optimization. What we are talking about, we have to optimize that function. That is the thing. But what are the challenges are the real world optimization problem. The challenges are, most of the problems are actually NP hard. I guess here you know about NP complete and NP hard. So if you have any confusion, please let me know. Let me discuss that one also. NP hard. So as for example, the polynomial, any decision problem which can be which can be completed in polynomial time, we call it P. I mean, we call it P, polynomial time problem, P problem. And non-deterministic polynomial time problem is what is something? Suppose a class of decision problems for which the potential solution can be verified quickly, even if finding the solution itself might be very difficult. For example, if you are given a long list of numbers and asked if any subset of them adds up to a specific number. So that is something, I mean, a very long array. Yeah, there is a noise. Yeah, thank you. So that is the non-deterministic polynomial time problem. Now coming to the NP hard problems are considered any problem NP hard which at the same time, I mean, NP complete and NP hard. Let me tell the NP complete first. If it meets two criteria, if the class is NP, that is potential solution can be verified very quickly. That is non-deterministic polynomial problem. That is called NP complete. And among the NP complete also comes if it is NP hard. That means it cannot be verified very easily. That is called in polynomial time. That is the NP hard problem. So as for example, I'm giving you one example. Like, I mean, we know that in computer science, the well-known examples like traveling salesman's problem is NP hard, knapsack problem, or the Boolean satisfiability problem. Okay, so those are NP hard. Now, in quantum computing, most of the, I mean, we actually want to solve those kind of NP hard problems. Now coming to the optimization in quantum computing. So, I mean, why it is challenging? Because the classical algorithm, they actually rely on the heuristic. Most of the time they are heuristic dependent. They can't guarantee finding the absolute best one. So how quantum computing can help? As I have already discussed, the core idea. So I mean, here we are using the superposition and entanglement, some of the distinct features which are not present in the classical computation. Now, in optimization in quantum computing, so here I like to first discuss in this discussion that what is an annealer, quantum annealer, because annealing is or the annealer is something we'll be using for solving a or optimizing a solution. Okay, so what is actually a quantum annealer? So we know that, I mean, the quantum annealing, you can say it's a meta heuristic for solving the QO problem. QO, I mean, again, QO again, quantum unconstrained binary optimization form. That means any problem, any NP hard problem, before putting it into quantum computing, what we are doing, we are that is, I mean, huge research. There was huge research. We are actually converting into a form called QO, that is quantum unconstrained. As I told you in the title of this particular lecture, I told quantum unconstrained. We don't want to keep any constraint. Quantum unconstrained binary optimization. That is, we have to encode into some binary variable, and that is called the QO problems. Now, quantum annealing is a meta heuristic for solving the QO problem, for finding the global minima. As I told you, in most of the cases, the problem optimization or the solution gets stuck into the local minima, or there could be multiple local minima or multiple global minima. To get rid of that one, to get into the for that one, there are a lot of, I mean, we know that in Adam optimizer and those things are there in machine learning, but in quantum computing, what we need to do, we use the optimizer, and that discussion will be coming into the Grover adaptive search. How we'll do the Grover adaptive search. So there I will discuss, and before that, the implementation of this optimizer will be the quantum annealer, which is a meta heuristic for solving the QO problem, for finding the global minimum using quantum fluctuations through an objective function. So same objective function which I was discussing, that the loss function in any optimization problem. Quantum annealing was formulated in its present form through a proposal in different form had been made in a closed system setting. The adiabatic theorem of quantum mechanics provides a guarantee that quantum annealing will find the final ground state if the runtime is sufficiently large relative to the inverse of the quantum ground state energy gap. This may appear a little bit, I mean, complex to you, but let me uh, tell you one more thing before coming to this. That is, you know that quantum hardware and those things are very tough to get. So, I mean, uh, there are certain research or there are certain implementation already we have done, because as you know that most of the implementation, and I'm from industry, and I don't know, I mean, maybe most of you are from academics. So let me give you one uh, insider news, that most of the quantum computing implementation in today's world are happening in the communication domain, that is telecommunication domain. And as you know, the 5G is going on, the rest of all the 7G or 8G, that work is going on full fledged. And 7G 8G what will be coming in future, that will be there will be some quantum computing. And that quantum computing, I mean, there we won't be using the, I mean, fully we are don't like to use the quantum hardware. That will be a mixture of the classical hardware, and where we'll be using the quantum computation optimizer, and quantum computation algorithm will be running into the classical system, and it will be a mixed and match of the classical and the quantum computation or the annealer. Now, coming to the quantum computing different algorithms or the this kind of optimization algorithm, there are something called variational quantum algorithm. Just to give you some knowledge, that it is a quantum circuit which also, as I told you, that uses the classical computer and then measures the output of the quantum circuit, calculate a loss function. The same thing, the loss function we use, and uses the classical optimizer to adjust the parameter. So here, I mean, the loss function and the optimizer is a classical optimizer. So that's why it's bit slow. That is the, performance we have seen. Now, there are certain other algorithms like quantum approximate optimization algorithm, QAOA, designed specifically for combinatorial optimization problem like max-cut. It alternates between the two types of operation to find a good approximate solution. And there is one more, variational quantum eigensolver, originally for quantum chemistry. And it can encode an optimization problem. Now, as I told, that quantum inspired algorithm, the, I mean, for a if I want to use a true quantum computing algorithm, I mean, it is very, the in a classical computer, it's a, I mean, we never get the performance on the classical computer. That is that I can tell you, and you can understand from your experience also. So that's why what we do, we actually mix the quantum algorithm and classical algorithm together, and we use the annealer as well as the classical hardwares. That is the way how we actually work in this kind of situation. So the quantum speed up, as we told, I mean, it is given in italics, that's why I have given. So while the quantum offers a theoretical speed up, providing definitive quantum advancement over the best classical algorithm for a practical large scale problem, remains an active area of research. Still researches are going on, but a combination of classical and this quantum algorithm in classical system, that has been accepted by industry. Now, coming to the Grover adaptive search. But before coming to Grover adaptive search, I like to tell you about the what is Grover search, and then I will jump into the Grover's adaptive search. So, any question so far?
question from the participants? Sir, please continue.
Okay. So Grover search is, it's actually a searching algorithm because it was initially formulated in the context of finding a single state of interest in a superposition of n qubit quantum states. As you know that the quantum states in a normal, what are the states? That could be a question. I mean, in a states in a quantum computing means, there is a superposition between 1 and 0. So, that's why we use the Hamiltonian. Here you'll find I have in many places I have written the Hamiltonian here. So the Grover search is often described as a search algorithm. To formulate in the context of finding a single state of interest. So our intention of finding a single state of interest in among the superposition of n number of qubit quantum states. The algorithm has been generalized to the case of multiple states of interest, in which case it is better interpreted as a sampling algorithm. So what it does actually in Grover search algorithm, it amplifies the amplitude of the states of interest within a large search space. So that is the trick it uses. It amplifies the,
Sir?
Yes.
Hello, sir?
Yes.
So please give one analogy about Grover search and then proceed, sir, because it is very new topic so that we can understand, sir. Because we know binary search, we know linear search. The Grover search is something is different. So give one analogy and then continue, sir. Thank you, sir.
Okay, thank you very much. So if you want an analogy of Grover search, then I have to show you the do you know about the oracle? Okay, so in quantum computing, there are phase of amplitude, phase of the amplitude of the target state. Those oracles we use in quantum computing. And for initial superposition, we use the Hadamard transformation. So, okay, fine. As for example, if you want an analogy, suppose we want to use the Grover search in case of traveling salesman's problem. Okay, so suppose in classical computation, for finding a specific element out from a set of n elements requires n tries. Okay, so there are n elements, and we want to find a specific element, so there will be n tries. Then the complexity of the for that operation will be order of n. Are you fine? Now,
yes, sir.
Yeah. So in Grover search algorithm, however, we can find a specific element out from a finite set of n element with complexity of order of root over n. So that is the difference here. But how we are finding out that calculation? For finding it, we use something called Grover's operator, where actually we use some this quantum superposition and oracle and Hadamard gate, that I can show you the equation. So there what we do actually, quantum Fourier transform, right? In what we do in the first Fourier transform, so in the first Fourier transform, what we do in that circuit, the entire circular circuit, we put the Grover's oracle, and we try to find out the exact match using the minimum oracle. So that is the intention. So for doing that, I'll just switch from here to one of my paper. Yeah, you can see here. So the Grover's algorithm, the initial superposition we are taking, we are giving input to the Grover's algorithm is a set of n qubits where 2 to the power n, I mean here it is binary 0 or 1, anything will come, so it will be 2 to the power n equal to n, and then that actually boils down to this calculation, that is 1 by root n. So this is the final calculation we actually obtain, that is a root n, and that is how the that root n, order of root n comes. So that is the maximum thing I can explain it here. And so now before coming to Grover's algorithm, let me discuss some of the things that there is also something called generalizing the Grover search. So in Grover's algorithms, that starts with uniform superposition of all computational basis states obtained by a set of Hadamard gates. Let me get into that paper once again. This is the transformation using a Hadamard gate. According to this is something, a paper which a research paper which is not published, and here we have done certain work where we have used the Hadamard gate, and this is the I mean the expression of the Hadamard gate. You know bra and ket 0 and 1, I mean by root 2. Okay, and then we come to this one, putting together, we come to this D equal to this one Hadamard gate operation. This particular expression we are getting, this is actually we call a diffusion, we call diffusion operator D. Okay, so and the entire thing will be repeated n number of times, and the as many time we are repeating, as long as we are not getting our solution, the targeted state, I mean it will be repeated, and that is that entire process we are calling it as a Grover operator. Now so that is what is called the Grover operator. Now I'm coming to some generalization of the Grover search. So as I have mentioned that Grover's algorithm start with a uniform superposition of all computational basis states obtained by a set of Hadamard gate. However, this is not strict requirement, and it can be replaced by any state preparation circuit which produces a distribution over the states that are relevant to the problem. So the equation is much, I mean the D equal to what I have shown, that comes to a much simpler equation. So I am just coming to that. The next topic, I actually come to that, the Grover adaptive search algorithm. Grover adaptive search algorithm. So in the Grover search algorithm, what we are doing, I just reiterate, we are taking the initial superposition and we are taking the oracle, and then what we are doing it, we are using the Hadamard gates. I mean the phase amplitude of the target state is inverted by the application of unitary operator called oracle, where X is the register that contains the item from the solution space, and the second register is transformed using a Hadamard gate according to the diffusion operator. So diffusion operator, what it does, the expression just now I have shown you, it gives this expression what I have highlighted, and this diffusion operator that amplify the amplitude of the target state, and this iteration continues, and this entire thing we are calling Grover operator or the Grover search. Now this Grover search, I mean this is actually again got some adaptation. So that adaptation will be calling it as a Grover adaptive search algorithm. It was first introduced by Dar and Wares, and that's why it is called also called the Dar and Ware algorithm. So Grover introduced the Grover rotation operator. There is something also called Grover rotation operator. This is a repeated application of which can be used to move from equal amplitude test, which is simple to prepare within a quantum computer, towards the states encoding the unknown marked points. Dar and Ware presented this algorithm based on Grover's method. So what we are doing, I again reiterate, our intention is that amplitude, we have to increase the amplitude. That is what actually the Bayesian this likelihood function or the Bayesian iterative method they do in the that probability distribution. If we increase the amplitude, actually the likelihood of getting the similar, suppose in some probability distribution we are getting two similar calculation we are getting, where the Bayesian iterative methods will find out or compare the um, attributes of the two results to find out whether they are unique or not. A similar kind of things we want to do it here, where the first thing is that we have to, if there are some equal amplitude test state, the first thing we have to do, we have to increase the amplitude, and then we have to find out whether we have to compare the amplitude test state to find out these attributes are equal or not, and this thing will be repeated as long as we are not getting our desired result. So that is actually what the Grover's rotation operator we are calling. And this Grover's rotation operator, the same thing Grover search we are doing in a rotational method, where the difference is that here we are comparing the likelihood of two results with depending on certain uh, attributes. So that is the difference over here. Now, while we are doing this, we are again repeating. So whatever Dar and Ware algorithm they have explained, that thing is nothing but the Grover search algorithm, where they are using the rotation operator, and that rotation operator they are doing iteratively into some likelihood function. So that is the difference between the normal Grover search and the Grover's adaptive search. Now, coming to Dar and Ware, they introduced this strategy for the selection of the iteration count based on random selection of number from a set of integer number. This set starts with 0, the only element. When the search is unsuccessful in finding a better solution, then algorithm, it adds up more element to maximum, that is from 0 to m minus 1. So each search step, what we do until a solution, the better solution, suppose in first search we are not getting the desired result, then what we're doing, we are increasing from 0 to some m minus 1, we're increasing the distribution to in order to get the correct solution. As long as we are not getting the correct solution, we'll be repeating this thing. Thus, the probability of selecting the right iteration count for a successful search increases. So this is something what we do in Grover adaptive search, and that algorithm I have been given over here. Any questions so far?
No, sir.
Okay. So before coming to this, let me jump into my paper once again. This is something I want to discuss, that how we have or what is the way of implementation of Grover's adaptive search. So a very easy way of implementing the, or not only the easy, actually that is only the feasible way, that we have to use the classical computation. And for any particular problem, first we have to find out the cost function of that problem. And if we find the cost function of the problem, what we need to do, the cost function will be running in the classical computation, and that will be run in the classical computation. And there will be a data transfer from classical computation to the quantum computation. So what we are doing, we are transferring, I mean, whatever result we are getting in the cost function, that is, we are giving the input to the cost function, and then after giving the cost function, the input whatever we are giving, after running it for several times, which is not given over here, we are actually transfer the entire equation and the result into the Grover algorithm. And this could be the same thing, can be, I have written here Grover algorithm, I haven't written any Grover adaptive search or whatever it is, because the same thing can be done with Grover search algorithm, generalized Grover search, or Grover adaptive search. So anything can be done, and that thing is actually coming into the quantum computation. And that thing, when the quantum computation is coming here in the picture, that thing you can run in a quantum hardware, or you may not run in a quantum hardware, that can be run into some parallel computation, where you can use some GPUs, and you can use some message passing interface, that is MPI. And using that, you can actually make it very fast to run the Grover algorithm in that scenario. And after the Grover, it runs the cost function, we run the Grover algorithm. To optimize it, we make a certain testing of whether the algorithm is matching our intention, that whatever we want or not. That is, here we have shown as the measurement. And when it comes into the measurement block, then we after the measurement, I mean, we see that, okay, here it is something like our this AI model. When we give the input, and the entire this the function, what is the cost function which is there in the AI model, we pass it through that, and there are weights and those things, the adjustments are there, we get some output. And then we see, I mean, we have our desired output, and we see that whether the, I mean, we adjust the weight and other things, and we see that whether the desired outputs are coming or not. And for that, actually what we need to do, we do the back propagation, and that is what is, I mean, we call it learning. And here we are calling it as measurement. The same thing we do, and we see that whether it is coming to our desired output or not. After that, in AI, what we have, in AI we do the testing. Suppose the model is ready, after that what we do, I mean, model is ready means, what I'm talking about, the model is trained. After the training of the model, what we do, we test with some sample data, and we see that whether it is, I mean, we give a measurement of some accuracy, F1 score or something like that. So here the same thing we do, I mean, with the sample, and we see with the sample and testing, here we see that whether that accuracy, desired accuracy or not. If it is not, that is the question. If it is not, so here the bifurcation of this line, that is the entered thing, is the classical computation, and the right hand side what I am having, that is the quantum computation. So the entered thing is running in the classical computation, the testing part is being done on the classical computation. And if we see that the desired function, desired result, we couldn't reach the desired result, we update the cost function. And if we update the cost function, the entered scenario got changed. Means whatever we have started with, whatever function we had, the entered thing got changed. And most of the time it is not a very huge change, it will be a very minor change on the existing function. And then we get into again the same loop, we do the iteration. And this is something what we are doing, that comes into the form of Grover adaptive search. That means we are iterating the same cycle again and again, as long as we are not reaching our goal. And most of the time this iteration doesn't take, I mean, it won't be I mean huge iteration. It will be, I mean, kind of very I mean very brief, maybe some, it comes to some 100 or maybe 500 iteration, we get our combinatorial optimization search. So that is something I wanted to discuss in today's discussion. And if you have any question, there are a lot of things like quantum dictionary that also I want to let me just, so quantum dictionary, I want to just give a brief about the quantum dictionary because the it is, you can say that is a dictionary circuit for most of the time we use for this kind of work. So it is built by the entangling two quantum registers and to represent respectively the key value pair. The idea behind quantum dictionary is to encode the value of a function. So that is the thing. So how to encode the value of a function in the phase of the value of register corresponding to every key doing something similar to quantum phase estimation, and reconstructing the value in computational basis with inverse quantum Fourier transform. So again, that inverse quantum Fourier transform, where you can see the same block diagram in Fourier transform. If you are familiar with the Fourier transform or the inverse Fourier transform, you can represent it with a block kind of diagram. Block diagram means something like, I'm talking about this one. Okay, so some kind of block diagram, we can come into the block diagram to represent the quantum dictionary. The values are mapped into multiples of a base angle. Given m qubits for these v, it is possible to represent 2m integer values as multipliers of 2 pi by m, where m, the capital M, is equal to 2 to the power m. So that is what quantum dictionary I wanted to discuss. So with this, I am coming to the very fag end of the discussion. Now, I mean, let me take some questions.
Hello, sir. Am I
Yeah.
audible?
Yes, yes, you are audible. Tell me.
Yes, sir. Thank you so much for an informative session. Sir, I have a question that we are using here hybrid type of things, right? That some
Right.
computation is performed on classical and optimization we are doing on quantum computing, quantum computers, right? Using, for example, you have shown Grover search algorithm. Now, my first question is that when we are having suppose some optimization problem, like unconstrained binary optimization problem, and we have to find the minima of this, right? Minimum, we have to minimize the function, and you said
Right.
that for minimization we have to find the we have to use Hamiltonian function, which will give me the
Right.
minimum energy, right? Now we
Right.
are using
Right.
Grover's algorithm, search algorithm. Basically here we are using we are amplifying the state in which we are interested. So here I am confused that on one side we are saying that it is minimizing the function, on other side when we are using Grover search algorithm, there we are actually maximizing the amplitude. So how both the things are related, I'm not able to get it. First thing. Second thing, here first thing is in the classical bits, and here we have converted into qubits. So how the classical bits, I mean bits, are converted into qubits to run the Grover's algorithm. So is there any encoding method used to convert bits into qubits and back from qubit to bits? So which method is being used? And third question is, as you are saying that adaptive Grover search, so actually we are using Grover search, but for testing whatever result is coming, that is being given back to the classical system. Then classical system is updating the function, right, to loss function. That's why it is called as adaptive Grover search, because Grover search is the in the feedback path, right? It whatever results are coming from the Grover search result, they are given back to the classical algorithm, and then updations are done. Then again the process is iteration is taking place. So that's why it is called adaptive search. So these are the three different questions I'm
Yeah,
having.
very good questions, madam. Very good questions.
Thank you,
So
sir.
let me come one by one. If I confuse with any question, I may ask you once again. Okay, please
Yeah, sure,
unmute.
sure, sure.
Yeah,
Yeah,
please
yeah.
unmute yourself. Okay, this is a rather a very good discussion. Let it be a good discussion. Okay, the first thing, let me tell you, we are not using the quantum hardware. The entire thing till now, whatever, I mean, Google has shown you the fast quantum computer and those things, those are still are very I mean, unstable,
Premature stage. Yes, sir. I
premature
understand.
stage. We are
Yeah,
not using any quantum hardware. This is the first
correct.
thing, ruled out. Quantum hardware ruled out. So whatever I have shown you, that is a, a section between a transfer of data between classical computation and quantum computation. Okay,
Hmm.
so you understand that there is a difference between, I mean, you have rightly pointed out that question, very good question, that we are switching between classical computation and quantum computation. So when we are switching between, that means in quantum computation we have lot of things, right? Entanglement, superposition, all those things we are having. And most, I mean, other than that, there are a lot of other things also. I mean, we can't send the data directly from classical computation to quantum
Quantum
computation.
computer.
Yeah,
Yes,
for that we use the encoding. You are right, there we are using the encoding method. We encoded it, and after encoding it we send it to the quantum computation. And the same thing, when we send it back to the classical computation, we use a decoder. So there
correct.
is a encoder and decoder in the entire cycle. And now the what was your last question?
So which type of encoding is used to convert this from bits to qubits? Which type of coding? For example, 0, 1 is there. So we have
Hmm,
to convert again into the qubit 0 and qubit 1, right? So
hmm,
how many number of bits are combined together, classical bits to make 1 qubit? Or
hmm.
matlab, what is the process? Is there any standard method by which we can convert our...
Obviously, very good question, madam. Very good question. So, classical decoding method. I mean, that is something actually I have discussed at the beginning of the thing, that we have the classical decoding method like a maximum likelihood decoding. Okay,
Okay,
so and we also have the soft decision decoding.
okay,
Okay, so here actually what will we do? We have to use the quantum unconstant binary optimization form. Means the entire thing we are converting into QO form. That is the quantum decoding. When we are doing the quantum decoding, there is a method, and there is a lot of research in that area also. So in that field, it that QO itself is a, I mean, we can take, I mean, hours, several hours of discussion on QO. We convert using the QO form, and using that QO form we convert it. I mean, actually what we do, we usually estimate the Euclidean distance. In soft decision decoding technique, we provide the we can provide better error correction capability than hard decision decoding. Okay, and after that we use, can can somebody mute it? Okay, so after, so what we do, we use a maximum likelihood decoding to eliminate the error. So when we are converting from classical computation to quantum computation, we have to add, you understand that the 1 and 0, that thing, I mean, when you are converting it, the states, actually the problem comes when you are converting the state from classical state to quantum state, and there will be huge error. And to, I mean, get rid of the error, to eliminate the error efficiently, we use the maximum likelihood decoding. Okay, and there we use the calculate the decoding, and to, I mean, to calculate the maximum likelihood decoding, we use the Bayesian identity probability. I mean, it's a pure probability, probabilistic calculation for the Bayesian identity. It is called, it is a Bayesian method. I mean, the heuristic, uh, how many whatever your decision divided by estimation probability of that, I mean, the way we explain the Bayesian, I mean, that's why we need some whiteboard. I mean, anyway, so the same thing we are calling it Bayesian identity because we are iteratively, I mean, we iteratively repeat it in encoding and decoding method. So the encoding and decoding method itself actually a huge computation, and there we use the high performance computation. I mean, you can imagine that is array of I mean GPUs will be using to implement that thing using a message passing interface. So that is encoding and decoding. You had another
Okay,
question.
okay, sir. So in your simulation, whatever paper you had shown, in that simulation, you must have converted your data, classical data into qubit, right?
Yes, yes, I'm
So
coming to
which
that paper.
particular decoding technique you coding and decoding technique you have
Max,
used?
maximum likelihood coding
Maximum
and
likelihood decode.
yes,
Okay,
yes,
okay.
yes, using the Bayesian identity.
Okay.
Okay.
Sir, this paper is available online?
No, no, no. This is, I mean, these I mean, very latest paper. I haven't published it.
Acha,
I'll be
okay, it's not
publishing it.
published yet. Okay,
Yeah, yeah.
okay, no problem.
And one more
Sir,
thing,
huh.
you had a last question. One more question you had asked,
My
right?
question was why we are telling that it is an adaptive Grover search, because here in the quantum computation part we are having Grover's algorithm, right, which is
Hmm.
finding the see, Grover algorithm works like we are amplifying the amplitude, right, amplification of
Right,
the
right.
amplitude.
Oh,
So
that is
here
that
we are
question. Correct.
increasing the amplitude, but here
Hmm,
we are
hmm.
saying that we are finding the minimum energy of the system, right?
Right.
In order to minimize the function. So how the two things are related, that I was not able to understand. Uh, I was not able to correlate the two things, because here the which I want to find or search for, that I am doing the amplification, right? In case of Grover search algorithm. Now whatever result is coming, that will be fed to the this system on the left hand side, update the constant, because it will give me some weights and something, some biasing and all those things are to be updated. So what the result will be, Grover's algorithm result will be the item in which I am interested, right, or the item in which I want to search it, that will be given as a sample to the update the constant function. So this is the maximum one, and here I am saying that I am minimizing the cost function. So so I am not able to relate the two things.
Very
Sir,
good.
you
This is
got
also
my question. You got
no, no.
my question.
I got your question. This is also a very good question, but there is a confusion. You got confused with something. Let me clear you. The first thing, let
Okay.
me clear you. Here in this picture, what I have shown, I have written Grover algorithm. In place of Grover algorithm, you can put Grover adaptive search, Grover search algorithm, or generalized Grover's algorithm, whatever it is. And
Okay.
we are repeating it, I mean, again and again.
Okay.
So that is the thing. That is the first thing. Second thing, you are telling, I mean, I told, I mean, or that is actually what Grover search algorithm says, it amplifies the amplitude.
Correct.
Okay. So for any this cost function, what we need to find out, we need to find out the global minima, right? Am I right?
Correct. Correct. Correct.
Now, when you are finding out the global minima, there could be in maxima minima. I mean, you think of our this what we have studied in our student life.
Hmm.
Okay,
Yes.
any equation, we do the first time derivation, then the second time derivation. We see that whether it is greater than less than zero or not. All those things we do, right? Now
Okay.
there could be multiple global minima. So that is a confusing thing. Another thing is that most of the time we see the cost function what we are working that gets stuck into a single local minima. It
Correct.
don't progress. That is the problem even in AI.
Right.
AIML also we have the same problem. That's why the Adam optimizer today, you can see the Adam optimizer which has come into existence. There was gradient descent algorithm, then stochastic gradient descent algorithm, then the you understand, right? I'm from gradient descent to
Yes, sir. I know.
stochastic
I
gradient.
know those algorithms.
No,
Yes, sir.
just imagine it. Just imagine it. That's what I'm telling you. I mean, the function of the function of those things. What is called that? F dot x y equal to the function of f dot x. What we are finding out, we are actually finding out the global minima. In order to find out the global minima, we are actually working on the, I mean, multiple local minima. From the local
Okay.
minima, we are progressing and we are finding out the global minima. But the problem is when we get stuck into the local minima. So when we get stuck into the local minima, one way we can do, I mean, for searching that, we can amplify the amplitude. If we amplifies the amplitude, it will be easy. See, our aim is to find out the global minima. We are still finding out the global minima, but we are not actually increasing anything. I mean, we are increasing the search space, nothing else. I mean, our intention is global minima, it is still there. That only we are searching, but in order to make it quickly, we are just increasing the search space. That is the thing. That is what we are doing. So what it is doing, I just reiterate once again, it amplifies the amplitudes of the states of interest within a large search space. Just to, why it does, just to increase the probability of measuring one of the target states. That is the only intention here, nothing else. So that
Yes,
is the
sir.
confusion you had. Am I clear, or should I?
Yes, sir. Yes, sir. I understood. Understood. Okay, so
Whatever
here we can
possible.
so
Yeah,
in quantum computation part, we can use any search algorithm, not a specific gravity Grover's algorithm. And
right,
thing is that
right,
we will iterate it so many times so that it will become adaptive, right?
right, right,
Right.
right, right,
Okay.
right,
Okay. Okay. Okay.
right. That is the. Thank you very much. Anyone else?
Thank you, sir.
Thank you. Anyone else? Any more questions?
From the participants? Then I have a question, sir.
Yeah, sure, please.
The topic is new to us, so the question is also very basic.
Yeah, please.
Actually, we heard that there are two major quantum algorithms for optimization problems. One is quantum approximate optimization algorithm and another is quantum annealing.
Hmm.
Is it so?
Quantum annealing you are talking about?
Yeah.
Yeah, with quantum
These are the
annealer.
two,
Yeah, please go ahead.
these are two methods of quantum optimization. Is it so?
There are more, but these are two, you can say. Yeah.
Major, these two are the major one.
Major one, yes. I
What is the
have,
basic?
I have. Yeah, please continue. I am just coming into that. Yeah. Quantum
What is
annealing.
the basic difference between these two?
Okay. So quantum annealing, if we talk, when we talk about the quantum annealing, we are actually, I mean, see, here in the both the cases, we are dealing with the complex combinatorial optimization problems. Okay. So there, what we are actually doing here in the quantum annealing, we are using the unconstant binary optimization. Okay. And we apply them to two parameterized families of planning problem. Okay, so actually the two problems comes something like that: navigation time, we call it navigation type, and scheduling type. Anyway, that is another complex part. But um, so what we do, I mean, this quantum annealing is more close to something what I was discussing, that finding the global minima among certain local minima. What we know, I mean, the normal way what we do in maybe stochastic gradient descent algorithm. Uh, don't get into any, I mean, programmatic way. Sometimes we use the stochastic gradient descent algorithm, I mean, among the data set, sometimes we do, right? The way we do in the energy landscape, the same mechanism when we are using the decoding, cubo encoding, that thing actually implemented in the same thing when it is implemented in quantum computing, is you can call it as quantum annealing. Now you were asking about this variational quantum, this one, variational quantum algorithm, VQA,
Achha,
or this one, right?
this one, yes, yes.
Yeah. So here the other one, what I told, I mean, after encoding, the entire thing comes into quantum computing domain. So let me come into this picture. So here you can see, so cost function is there. After that, the entire thing comes into Grover algorithm. Okay. So the entire things after encoding, in between, actually, when it comes, some encoding happens in between. Okay. So entire things comes into the quantum computation domain. But in case of the other one, we are not doing the entire thing in the quantum computation domain. There will be a part will be doing in classical computing domain and part will be doing in quantum computing domain. So whatever I have discussed here, that is variational quantum algorithm, it is actually a hybrid. It's a hybrid algorithm. So it's both quantum, combine the quantum computer as well as classic one. And thing is that the two things here, you will get two problem. One problem will be there you won't get the good performance. Another thing is that there are, I mean, whenever you are doing a part into quantum computing and part into classical computation, there will be encoding and decoding. If there are more encoding and decoding, it will take more time and the performance of the entire thing will get reduced. So that is the problem.
So, sir, when we will consider the annealing and when we will consider this the variational VQ?
Yeah, it's depend on what. This is a very good question actually, and that a question which comes to the industry. When we will consider annealing and when we will consider VQA, the thing is that for implementing quantum computing, it requires lot of libraries, softwares, and other things. And many time, and in many cases, we have seen there are some proprietary libraries like D-Wave, then IBM. They have the proprietary libraries. Okay, now there are not all, now there are some. I mean, when we are doing the implementation, the companies for whom we are doing it, we have to estimate some of the things, how much price, I mean, how much price we have to, I mean, invest on making that particular software, because human resource is a huge investment. Other than human resource, actually most of the companies, they want to reduce the cost from royalty and other things, buying softwares, royalties and those things. So when we see that the libraries and those things, I mean, we can't meet that thing, that time we do something like that, we compromise on the performance and we do a mix and match, that is the mixture of classical and quantum computation, mixture of both the thing. And also, it's a very good question, that's why I told. Also, if we see the problem, the problem which are dealing is not that much complex. In financial domain, most of the problems we deal with a combination of classical and quantum computation. And in most of this other thing means, I'm telling you, there are a lot of high performance computing which deals with this simulation of these astronomical softwares. There are a lot of astronomical softwares, meteorological data. There are a lot of computation required, and there and one more thing we have to keep in our mind, that whether it is constant on time constant or time critical or not. If it is not time critical, we take the variational, means okay, let it take time, doesn't matter, I want the result. And if we see it is time critical, we need the result very quickly, that is in communication domain. Suppose I am calling you, and if the calling takes half an hour time for calling somebody, you won't like it, right? That's a very natural thing. So that, I mean, when I'm calling somebody, the resource allocation and everything has to happen within 1/10 second. Within 1/10 second, everything has to happen. So it is very, very time critical. So there is something you can see, what we loosely call the telephone tower. That is actually, we call it E node B. Through the E node B, when it goes, the antenna actually, it does that resource allocation. And due to that time critical, we use the quantum computation fully. We don't use the variational over there. So in brief, I can say, in case of time critical, something like that, mission critical, something like that, this missile or something what we are doing, I mean, which is time critical, or telecommunication, mostly what we have done, we use the that QO and mostly the quantum computation, and we don't do much encoding and decoding. And if it is not time critical, we take variation. So am I clear to you?
Yes, yes, yes. Although the things are new to us, but it is okay. And another question,
Please.
basic question, in terms of computational complexity, which one is more efficient?
Computational complexity is actually, I'm telling you, this entire quantum computing is new to us. And our thinking, our way of problem solving, all, see, at the end of the day, mathematics is nothing but a way of solving a problem. Think of that, to finding of the square root, what we have learned in our school or at home, whatever it is, the way, I mean, without using a calculator, we can find out the square root. But when I went to USA, I have seen the people, they don't know that method, but we know that method. And that is a traditional computation method in India. We know a lot of things. I mean, in one line, I can do the multiplication of some 4-digit number into 4-digit. So those Vedic mathematics or whatever, those are traditional mathematics. So what are those? Those are certain systems of doing the mathematical thing. So here now, I mean, so this computation is also same thing. The classical computation is a type, is way of problem solving, following certain rules and algorithm, whatever the Boolean algebra, whatever we have been taught. Now, quantum computing is a new way of doing that one. That is a totally different way. So if we change our way of thinking, quantum computation is not complex. I mean, when we are thinking, when we know that our classical computation is easy, the quantum computation is also easy. And the day will come when quantum computation will be there. I'm not talking about the replacement of the entire classical computation, but we can start it from the maybe from second year of the competition, computer science courses, and then it will be easy. So it's not that quantum computation is complex and this one is simpler. It's just changing of way of thinking. That's the thing. That's what it differs.
Sir, actually, we are using quantum computers to solve the problems in classical, right? The problems which we cannot solve using classical, we are going for quantum, right?
Right.
So basically, it is good for computational things, right? But only thing
Right.
is that because of noise and other problems, we are not getting quantum supremacy. We are just showing the prototype that yes, it is possible using quantum also, right?
And
Uh,
you are right. And one more
and-
thing, just in your, I mean, sorry to interrupt you.
uh,
Here also, I tell you one more thing, that when we are converting that, the same thing, what we have discussed, encoding and decoding, there also we lost lot of data. That is also one of the, I mean, problem in the industry right now. Yes, please go ahead. You're telling something else. I have stopped you in between.
Madam has asked the question that whether it is which one is complex actually. So I wanted to add that see, we are going for quantum computing only for solving the NP hard problems. So basically, it is giving us speed advantage.
Madam, here,
Huh?
let me tell you, you can
Huh?
solve even the easy problem also by quantum computing. No, no
Yes,
one,
we can
no one
solve
will stop
definitely.
you.
Yes, sir. But why to use such a complex
I
or
agree,
costly
I
thing
agree, I
to
agree.
solve the simple
Yes,
problem if my
yes,
classical computer can do,
yes,
right?
yes, yes, yes.
Because my quantum computer is very expensive, so why to go for that?
No, no,
That is
no.
my idea. But
Again, I mean, maybe you are right. We are not using the quantum hardware.
yeah,
I mean, it is expensive in the sense the entire computation what we will be doing, we need the, I mean, classical hardware on top of the libraries and other things are coming into picture, and the classical hardware will be some network of GPU and those things, and that will be, yes, in that way you are right, that will be expensive.
Oh, yes, sir. One more thing I would like to ask you. You have shown your adaptive algorithm, adaptive Grover, sir. Have you tested it on D-Wave or IBM
D-Wave,
quantum
yes, yes, yes.
computer?
D-Wave, we have tested.
You have tested. So
Yes, yes, yes.
number of iterations, just like in Grover's algorithm, we require under root n, right? So
Yes,
how
yes.
many number of numbers? I mean, iterations are required here in your. Okay, these are the results. Okay,
Yeah,
probability
yeah, yeah.
evaluation, iteration 1, 2, 3, 4. Okay, okay.
So here I have given some 5 iteration, but we
Huh.
have done it at the, I mean, at least 50 or something like that.
Okay, so 4
And
qubit. You are having
uh,
4 qubit.
yes, yes, yes.
4 qubit convert. Okay, okay.
In paper, I mean, actually, we have certain constraint also for putting the company's data into the paper. There are a lot of, I mean, we have lot of constraint in industry, you know.
Sir, this paper is showing that it is August 2015. So it is
Yeah.
published. It is published, right?
Uh, a part of it got published. This
Okay.
particular one we haven't published. Actually, we have worked on it, and a for the adaptive of this one will get published.
Okay. Okay. Okay, sir. Thank you so much, sir. Thank you.
Thank you, thank you, thank you. Any other questions?
Hello, sir.
Yeah, please.
Actually, with respect, I have a very basic question because in the entire session, the two words are morely highlighting, that is adaptive learning and the system. So
Hmm.
I want to ask that if I want to do a classical reinforcement learning, in which what happens, entire separate environment is created, and in which the algorithm learns to predict something, and if it gets correct, so it rewards itself, and if gets wrong, it penalizes itself. Okay, so
Okay.
is, is that similar environment is created in QML algorithms, or it differs in some sense?
In QML, uh, not same. There will be little bit different when we are implementing that one. See, the thing is that it's not you can't do a one-to-one map. Okay, so if you are talking about reinforcement learning, a similar kind of maximization I mean this cost function. So in reinforcement learning, instead of minimizing, we maximize it. Okay. Uh,
Because both algorithms say in reinforcement learning or in QML also both use adaptive learning method.
right, right,
So,
right, right.
right. So I
So
just
that's what.
want to ask, because if environment say with respect to any parameter, say size or complexity, if the environment changes, how it will be compared with classical environment or environment quantum system. So I just want, is there any difference, or they same? Because there is much between silver lining, because we cannot use separate classical separate quantum algorithm or say classical. We have to do some hybrid system, develop some hybrid system. So how does it with affect a separate environment in classical system, or say in entirely new entire quantum system, or the hybrid of both systems with respect to environment created for adaptive learning?
Okay, for the this is also a very good question. For adaptive learning, when we are doing, as I told you, that we have to maximize. Okay, instead of minimizing, we have to maximize it. Okay, so that is the difference. And when we are doing that, the search space and the data what we have to handle, that will be huge. Okay, so now let us imagine we are just switching from classical to quantum computation with respect to this kind of maximization, like maximization cost function. Okay, and there we have to handle lot of data, and so the encoding and decoding will be huge in those cases. That's why instead of switching from classical to quantum computation in case of maximization problem, it's better to continue in the quantum computation alone, And then, I mean, to minimize the encoding and decoding is similar kind of thing. So if we can minimize it, then performance will be better. That is a very short answer.
Okay, sir. So I have got another question. If
Yes,
say
yes.
if I want to fine tune a large language model with respect to my construct or my hello, sir.
Yeah. I'm listening. Actually, there was some noise. That's why. Yeah.
So with respect to that, if I want to train my own large language model, so there are billions of parameters. So if you are saying it is feasible to train an entire new quantum system, so how it will be cost effective? Means will it be cost effective or not? It will be faster, I know, but
No,
will
it won't
within
be, Rushikesh. It won't be cost effective. That I can tell you, because in case of large language model, I mean, we have to handle billions of parameter, and as I told you, I mean, if we switch from classical to this quantum computing domain, there will be a lot of encoding and decoding. Rather than that,
yes,
the
sir.
similar kind of work, I mean, I have also extensively worked in this large language model training and other things. There, what we do, we use some other algorithm. I mean, I can tell you, it's kind of a petals algorithm. It's this torrent, we do when we download something using torrent,
Ye-
BitTorrent.
Yes, sir. Yes, sir.
So in
Yes, sir.
torrent, you know that, I mean, it never download from a single server. Instead of that, it, I mean, just think it as a tree, I mean, of different branches. Okay, it is
It
downloading.
diverts to a particular server.
Yeah. So the opposite of that we have to do in this case. I mean, whatever you are doing in torrent, the opposite of that we can do. I mean, it's a very, I mean, without any picture and other things, very tough to I mean, make you understand. But
I got it, sir. I got it. It's
yeah,
like a neural network between back propagation, I think.
back propagation only, but in a different way. In a different way, we
Okay.
have to do it.
Okay.
That's why the
So
all LLM.
it includes
Yeah.
it includes all the branches with respect to a single search or multiple searches.
Yes. And Rushikesh, one more thing I'm telling you, all these training of LLM, whichever companies they have done, I mean, they are following this kind of algorithm only, but they don't reveal it till now. They
Okay.
kept it, I
Okay.
mean, confined in their domain itself.
Okay. So okay, sir. Thank you very much.
Thank you. Thank you for the question also. Anyone else? Otherwise, Dr. Chatterjee, can we close it?
Any question from the participants? Any further?
Sir,
Yes.
so can you share any examples where quantum optimization successfully implemented in any industries?
Quantum optimization in industry.
Yes, sir.
Quantum optimization in industry, we have done lot of such implementation in case of, as I told you, in the telecommunication domain. So in telecommunication, this, I mean, most of the time we know only the service provider. As for example, you have connection from Airtel, or maybe you are having a connection from some other, maybe Idea or somebody. Anyway, so those companies are not the actual companies. There are some back-end companies like Ericsson, VIAV, these companies are there. And those companies actually, they work with these resource allocation and all those things. There is a huge competition background. And there, we are working on something like 6G or 7G. Okay, mostly in 7G, there are quantum computation comes into picture, and there we have used the quantum optimization. And in many such, there are something called MIMO. Okay, so in I mean, in many such implementation, we have used D-Wave. D-Wave, they have provided their stops and their circuit and other things, and we have used it. And the optimizer there we have used mostly these Grover's adaptive search.
So,
is
sir,
that yeah.
I want to add that
Thank you, sir.
is existing optic fibers are compatible with 7G or 6G for experimentation or transmission of the internet, or it requires new hardware? Because that will be more costlier to any company to lay down the another network. Because you understand my question, no?
I understand your question, but that is fully another domain. See, I'm purely from the back end engineering or the computer science domain, you can say. But again, the implementation comes into telecommunication and other things. Obviously, there will be some changes in the hardware and other things. Maybe you have to change your handset, and your service provider will change the E-node B, what you call the tower and the antenna. That obviously will get changed, right? Because when the 5G got implemented, you have seen from the user end there was some changes. Okay, you have to change your handset. Your handset should be capable of working with 5G. And other than that, there's a similar changes are there in the antenna side, because antenna has to work in that performance. You are right, but that is purely a total, I mean, a different domain.
Okay, sir. Thank you. Thank you.
Last 4 minutes we are having. Any other questions? Otherwise, we'll wind up the call. So, Dr. Chatterjee?
Sir, I am Chakraborty, not Chatterjee.
Oh, sorry. Okay, Dr. Chakraborty.
Okay,
Yeah.
no problem, no issue.
Yeah.
Many thanks for very interesting interactive sessions. Can you please provide some resource material to us, your PPT and resource material for the participants, because we are trying to learn the quantum intelligence from very basics. So can you please provide some resource material to us?
Yeah, the PPT I can send you, but PPT doesn't contain everything. Okay, that I will send you. And you also wanted some questionnaire, you told. Do you require it still?
The questionnaire, yes, we need it for the exam. But
Okay.
in addition to that, I am asking some basic resource material, because your PPT, we have seen that there are many things that cannot be incorporated in the PPT. No? So
Right.
Sir, I am Professor Day, the co-coordinator of this program.
Yes,
As
Professor.
mentioned, good evening, sir. As mentioned by Professor Chakraborty, this session is, and moreover, the entire activity so far we have been observing is very much, interesting, and participants are asking for some resources, some basic rudimentary resources from where they can start. They actually want to start from the scratch. They are very much motivated from the program. All the sessions so far have been done. So can you, sir, please suggest some basic rudimentary materials so that our participant can go for a kickstart of the subject?
Sure, I'll send, and also I'll send some of the links for courses and other things which will help them.
Okay. Then we can share this to the participants, and we also okay.
Thank you so much,
So
sir.
many thanks.
Thank you very much, and thank you all participant and Dr. Day, Professor Day, and Professor Chakraborty. Thank you. Take care. Bye. Good night.
Yeah. Okay. Good night, sir. With this, we are ending this session. Thank you, participants. We will be joining to the next session very shortly. Please.
In the next session, will be started 15 minutes late due to heavy raining in Kolkata. Some disturbances there. So
I'm dropping them.
Okay, sir. Thank you, sir. Thank you, sir. So, dear participant, the next session will be started from 7:45. Okay, the link is already mailed to you. We have again sent the mail to the WhatsApp group. Send the link to the WhatsApp group for the session 8.
Thank you so much.
Thank you so much.
Thank you, madam. we are closing the session.